Hi everyone, this is a lecture about Green's theorem, and it is a very important theorem. It's a fundamental result for some of the complex number phenomenon, and it's really fun to learn about this. So here's again, I have already posted several videos about the Green's theorem, but once again, I enjoy it teaching Calculus 3 and to try to explain once again. And this is going to be a lot simpler shape of the curve. It's about curve and the vector field. Its region enclosed by this curve. The shape of curve it can be more complicated, and in most of the textbook example, this will be sufficient. If it's not, we can demonstrate that it can be divided into this simpler shape. So let's begin with a simpler curve, and let's not worry too much about in full generality in terms of the shape of the curve. So curve we are considering in here is such that the curve can be divided into two pieces such that it covers the top piece and covers the bottom piece, all given by the function of x. It can have this vertical edge part. In that case, we can consider that as one single x value. So this is general enough. And also, we have to be able to look at the same curve and divide it into pieces right and left, such that there is this y value. Again, this could be horizontal line, and such that this portion is given as a function of y, like this, g2y, and the other part is given as a function of y as well. Two different cases. Think about an ellipse or a circle or any rectangle or any parallelogram. Any of the convex shape, it's fall into that kind of breakdown. So once we have this, and everything will go nicely without worrying too much about it. So that's it. So what I mean by the nicely, nice curve is such that we can divide this one into two pieces like that, over x-axis and y-axis. Positively oriented means if we recognize this part in here as interior, which is this region, part of the context, and as you go around with this orientation, the region must be on your left side. And you can see it here, the arrow is going in kind of in the same direction, I hope you agree, then the region is on your left side. If that's the case, we say this is a positively oriented relative to region it encloses. So that's the setup. As a curve-oriented curve, it's nice enough, and the vector field, and the region it encloses. And the theorem says the following. Green's theorem concerns the line integral of a vector field along that oriented curve. Here's a notation. There's no t or anything. It's recognizing its parameterization independence is actually equal to the value of this double integral. Dx dy is not iterated integral symbol in my course. In the book we are using, it's dx dy is a compound symbol. Order doesn't exchange. It's just to represent double integral. Rather than writing down specific formula of these components of f, I use this scalar curl. This is not curl. This is a curl with a zero in it. I just use this notation to recognize that this is some operation phenomena that it happens for more general cases. So if you look at line integral, if you push it up to double integral, there's this operational thing we do. So what are those? Let's see, if we write that vector field on this xy plane with x component p and y component q, that's the vector field, position vector field, then this double integral has this function inside qx minus py. So x and y kind of in the same place. X shows up first and y shows up later, but you have to swap this around. Q goes first and p goes later, and there is this negative symbol there. Where is this negative coming from? In my opinion, and after the series of lecture, it's really coming from negative reciprocal. So if the two lines are perpendicular to each other, the relationship to slope is negative reciprocal. In terms vector-wise, we swap x and y and put negative symbol 1 over there. So if you think about 90-degree rotation matrix, I think it's negative 90-degree of this matrix, you pick up something like this. So that's the statement. And I forgot this important condition. This F, the vector field in here, if you look at the left-hand side, it's very, very subtle part, and this makes a huge difference. It's something very important thing, it's interesting things going on. In the left-hand side, all that requires, this vector field is nicely defined around this curve. Left-hand side doesn't care anything about this vector field inside and there. Right-hand side, though, requires this double integral. Therefore, this vector field f must be defined everywhere inside there. So that is required. Whenever this is not satisfied, if f is not quite defined in there, something interesting things going on. Of course, we don't have this equality, and for some reason it's going around, and the fact that f cannot be closed up into the interior region such that it's not nicely defined. If it is not possible, then something interesting going on. Let me rephrase this thing again. Suppose you happen to have a formula that only works around this curve, and your formula doesn't quite extend to that. But someone else later come up with a nice way to figure it out, how to extend that function that only is defined around this curve, but kind of extended into this part, and figure out it's well nicely extended. Then this works. So it could be the fact of whether there is such an extension or not determines whether this is going to be possible or not. So even though this thing does not depend on what's going on inside there, this God-given statement, whether it's possible, not by me, someone else, or 1,000 years later, brighter person come up with a way to extend that particular function all the way inside so that it makes sense inside there, then we have this thing. But sometimes it's detected by this one, whether this equal or not. So because of that, sometimes this, if you measure this line integral in here, tells you that whether it's possible or not. If it's possible to extend this function, this is going to happen. This green thing is theorem is going to happen. So it has some consequences. If it is not possible, then we don't have that. And this line integral had a very special value, something like that. So I spent a long time to explain the subtlety is behind this equation. It all goes into the understanding the meaning of whether f is defined on D or not. Again, this only cares about C. What if I piecewisely define f? That has the same value on C, but has a different value inside to that. And then there's this, something interesting is going on. So it's really interesting. All right, this is already the part that I was talking about. If it happened that the vector field, and you do this qx minus py, I'm going to call the scalar curl. If your scalar curl is 0 on all the entire region inside, because it's extended and defined, and then the line integral is supposed to be 0. So whoever is brilliant enough and 1,000 years later be able to extend your vector field that only makes sense just around this boundary, but this guy extended into the interior, then this will happen. Therefore, it's going to be 0. But even if you cannot extend this, you can only calculate this the line integral, and you can still calculate whether it's a 0. But this is a sure sign that it can be extended into the interior region, and it is still curl is 0. So it is kind of detecting what happened if you try to extend it inside. It's a very mathematical, deep thinking into that, but in practice, it just has some nice consequences. Again, if you calculate this, look at the vector field, and calculate the curl as a 0, then your integral is simply 0. How nice is that? So here's the most striking feature of that vector field whose curl is 0, which is this condition there. If that's the case, and if you happen to have two different paths, the path is better than the curves at this point. Gamma 1 starts at P and ends at Q, and gamma 2 is a different curve, like I described it here, starts at the same P and the same Q, but through a different route. And if you consider these two different line integrals, starts and ends at the same, but in possibly different path, and this claims that line integral value of this line integral is going to be the same, as long as your vector field has this curious property, curl being 0, namely Qx is equal to Py. If you have that property, this wonderful thing will take place. For example, the key application is that if you have to calculate line integral over this crazy path, then you can just replace it with a straight line and calculate the line integral over straight line. That value is going to be the same as line integral over the crazy path. If you think about what I just said, it's just very interesting things going on here. But not all vector field is got to be curl 0 vector field. Right, here's some examples. Because it's crossing and differentiated with respect to x and y in that fashion, so that's Q, that's being crossed here, put it in the first place and differentiated with respect to x, that one there. You can see if it is only in terms of y, then Qx is going to be 0. If it is only in terms of x, Py is going to be 0. So it's easy to verify that curl of this vector field is going to be 0 always. So in that case, this interesting thing happens. So let's actually go ahead and calculate this line integral, not using the corollary number 2, but in an honest fashion, and see if you can actually verify the claim, the corollary 2 directly. So here it is. Here's a line integral. This would be directed calculation using the parametrization. The curve is parameterized by whatever the information, so that's why it's x prime there. So this is h comma k, that's a vector field, x prime comma y prime, whatever the curve formula, that's the dr dt part, so it's a dot product, as you can see. So you can separate that, as you can do this integral dt and integral with respect to just this part. So let's split the integral, then realize I skipped a little bit in here. So if you just look at this part in here and dt, and x is a formula like xt, maybe I should write this one down in here. Well, let's see how this one works. X is actually the function of this, function of t. So if you look at that part, it looks like this, h and x of t, h of x of t, and here's x prime of t and dt. So if you distribute that and think about that integral only, this is the, hold on, this is the integral we're looking at. Oh, forgot that it works different way. So to change from there to there, we can do a u substitution. If I call that one u equals x of t, or you can just write as a x if you're familiar with this. Then du dt, if you calculate that, that's x prime, and you can see x prime times dt, that's du. But you can go back to x notation, so you can write it, this integral, only in terms of x, as x is a variable, not dependent variable, as in here in terms of t. So this integral can be rewritten in terms of x like that. And the same for ky. So again, if you use a y substitution, this y prime disappears, becomes just y integral. And this limit value is going to be x values and y values. So when t equals a, then what is the x coordinate when t equals b, what was the x-coordinate of that point there, and the same. Now, this earlier corollary, or the Green's theorem, implies that this is going to be 0. It's actually this individual part is going to be 0. Because if this curve is going around like this, but this curve is supposed to be closed curve, if you start in whatever the point and then come back to that point, even though this parameter t equals a and t equals b is different, the point is the same. So xa and xb and ya and yb, they're all the same. So it's going from the same point, 5 to 5. The integral must be 0. Okay, so that's why I realized by looking at this above there, I forgot to explain why this is the case, the connection between these two. So let me explain. It's not that hard. If you look at this gamma 1, but that explains the first one, I think, right? Yeah. So I think I'm going to explain the second item, and probably I have example for that. Maybe not, but let me explain this one first. If you look at gamma 1, actually gamma 2, it seems like if you look at this as an interior region, so, well, let's assume that gamma 2 is actually nice like this, so that it's a simple curve, like we saw before. Then this, if you look at this as an interior region, that looks like positively oriented, because on the left side, there's a region. And if you look at gamma 1, if you just continue to gamma 1, it is not quite in the same orientation. So if you use negative gamma 1 for that one, so you go in gamma 2, continue to negative gamma 1, that's the same as this one-way oriented closed curve. Then it's supposed to be 0, but the other one was negative gamma 1. So if you move that to the other side, it becomes something like this. So for that to happen as a closed curve and being 0, the value of these two things must be the same so that they cancel out each other and being that. So that's why. The next one is really, really important example. It's kind of covers all the situation, is the gradient vector field. F is not a vector field. F is a scalar function, like a temperature function. You give a location, it spits out a number, a scalar function like a temperature. Then you can calculate, there's this gradient operator. Out of that scalar function, you can create a vector field, so that if you pick a point, that tells you the vector, where the wind is blowing or where the temperature is increasing, whatever the direction. So that's our F. If that's the case, it turns out that curl of this one is a 0. So let's calculate the curl. This is P and that's Q. You're going to take that one, Q, and differentiate with respect to X. So that's going to be Fy further differentiated with respect to X. That's a P part, and P is differentiated with respect to Y. So that would be minus Px with respect to Y. So by Clairaut's theorem, if f, this vector field is continuously differentiable, no, the scalar function f is continuously differentiable, then by Clairaut's theorem, these two things are supposed to be the same. So that's 0. So you can see that this appears, Clairaut's phenomenon is embedded in so many places. It is a fundamental reason why certain things are happening. Now, because of that, curl is 0. So if you do the line integral of this gradient vector field around the closed curve, is going to be always 0. And if you have looking at the two different paths from one place to the same beginning and ending place, their values of integral is going to be always the same, no matter what path you choose. So if the circle is convenient to parameterize, then use that. If the straight line is, for whatever reason, it's better, you can use whatever path you use, their value is going to be the same. There's something called the fundamental theorem of line integrals, and this will tell you more than what we got out of that. It just says the same, but this is a more specific version. From their formulation, we deduce the same conclusion. So don't think these two things are the same. The fundamental theorem of line integral actually tells you more. So it's the same context. You go from A to B. That's the line integral, a path, not necessarily closed, so it's general enough. Then how do we calculate it? Because it is the gradient vector field, you can calculate often in practice, not always possible, but there is the scalar function. If it is gradient by definition, if it is a gradient vector field, there is going to be the scalar function. Can we write this integral value in terms of scalar function? Just like going backward is not the same as anti-differentiation in one variable function, but here's the conclusion. Actually evaluate that scalar function at the terminal point. That's gamma b is indicating that terminal point. Where is that location of the path and the ending time? So plug that one in there, get the temperature, for example, out of there, and this f at the beginning point. Plug it in there. And the difference between these two scalar is supposed to be the value of this integral. So as you can see, in the context of what we have been discussing above, is that it doesn't matter what your path is. Only thing that matters in the right-hand side is a value of a scalar function at there, value of a scalar function at there. If you go ahead and change this gamma to some other crazy thing, going back and forth a million times and go forward, whatever, right-hand side says is all about the value of these two things. And then I was keeping this gradient vector field exactly the same and only changes gamma. And the right-hand side does not care what happens in between, is only beginning and end. It's really interesting to see these two different perspectives. If you look at the proof of this one, it has nothing to do with the Green's theorem or anything. It's a straightforward calculation, and it picks up that phenomenon here as well. They named this property path independence. It kind of makes sense. It doesn't matter what kind of path you choose, as long as you have beginning and end point the same, then the value of line integral will remain the same all the time, as long as your vector field have the property vanishing curl. That's the way to say it. So next part of the video is going to be proof, and I don't know, it doesn't use some interesting idea or anything, but it is really worth understanding the proof of this phenomenon. It's going to be the basis of all the other proofs, Stokes' theorem and divergence theorem.